Hello everyone, I'm Simon Mo, and today I'll talk about machine learning model serving. I'll give you an overview of what serving machine learning model means, what it requires, and after this talk, I hope you can take away some understanding of model serving landscape, learn common approaches and pitfalls, and learn about a new library having been developing to overcome these common pain points. So let's start with what is model serving, and in particular, where does it fit into the machine learning lifecycle? To build and deploy machine learning powered applications, we roughly have these three major steps. You develop the model, train the model, and perform inference on the model. Model development is where we collect the data, analyze the data, and iteratively improve the modeling. Once we have the model, it's pushed into training pipeline that learns from live production data. What happens then after we have several trained and validated models? These models need to be put inside a prediction service suitable for end user application. And the last stage is what we care about when serving machine learning model and deploying in production. So this talk will be structured as follows. I'll first discuss some requirements for model serving to get some overview of what a typical model serving workload looks like. And then I'll talk about two common approaches for model serving. These two common approaches roughly cover the current model serving solution out there. And then lastly, I'll introduce RayServe, a web framework built on top of distributed runtime Ray and that make it easy for serving machine learning models and scaling them to many machines while delivering end-to-end control over the prediction. Let's start with the requirements. What are some basic requirements for model servers? Well, first of all, it needs to deliver predictions. Given an input, right there we have a cat, it should run through the machine learning model and output the prediction and say, it's a cat. But in many cases, we have more than just one type of model. There's a need to multiplex different models, regardless of different versions, different algorithms, or different architecture. It is more than practical to use different models for even just the same problem. Different frameworks each have their own pros and cons and specialties. To solve the real world problem, we just grab the best tool available out there, and the model server should take care of multiplexing many different models. Another key characteristic of machine learning models is that they are quite slow and resource intensive. We don't want our user to wait for the request to pile up. What can we do? Model servers should be able to transparently scale the model to multiple replicas and no balancing among them, so requests can be parallelized. And despite being resource intensive and oftentimes slow, machine learning model can utilize hardware parallelism like vectorized instructions or multithreading to efficiently perform inference on a batch of requests. Many times, performing inference on a batch, say 4 images, only come with a very small cost compared to just one image. Batching is a simple technique to improve utilization and throughput of the models. When you put model in production, we often want to periodically retrain the model on fresh data or experiment with different hyperparameters. This is when versioning becomes an important requirement. Can serving system enable zero downtime deployment, gradual rollout or rollback, or A/B testing? Can we transparently update the version of the model or test a newer version without user noticing any difference? There are also requirements for handling pre-processing and post-processing logic for the models. Typically, our models accept numeric tensors and output numeric tensors. But this is not what end user wants. For the model, expect a validated transformed input. The output array of floating point numbers means nothing to the end user for the machine learning application. Therefore, pre-processing and post-processing logic is critical to ML model servers. And last but not least, we need to pay attention to how much performance are we getting out of the hardware and relative cost. Because ML models are computationally expensive, their relative throughput is slow. To handle large volume of incoming data, we need to trade off the cost, performance, latency, and throughput. Does your serving system allow you to tweak this parameter? Does your serving system help you optimize your cost given your performance requirements? And in summary, serving machine learning models have unique set of requirements. Now let's take a look at how people deploy models in production today. There are two common approaches to deploy models in production. I'll discuss them one by one. One approach is to embed your model evaluation logic inside a typical web server. And the second approach is to offload the model to an external specialized service. Let's take a look at the first approach. The first approach typically wraps the model inside a conventional web server. I'll use Flask, a popular Python web framework, as an example here. When HTTP requests come in, the Flask server can dispatch the request to different API endpoints. We can make one of the endpoint handler our model evaluation logic. Let's say we reach /API/image/predict endpoint. The input will be transformed and evaluated in a TensorFlow model. The output result is captured inside the return response. Let's take a look at some pros and cons of this approach. The web server approach is simple and easy to build and understand. It gives the developer end-to-end control over how the request is handled and how the model is served. If you're just doing a simple demo or proof of concept, this approach is perfect because it gets the job done. However, a big downside of this approach is whenever you want to scale more than just one query at a time or have multiple models to be served at the same time. The model is typically loaded as some sort of global variable, and there's no way to manage the startup, initialization, warm-up, weights loading, and other lifecycle of the model. And lastly, if one model crashes, it can bring the whole web server down. There are a few more hurdles to jump through with this approach. A typical deployment model for Python web servers is a process pool-based. This means requests are load balanced and run different instantiation of the worker process. As we discussed before, the model is typically stored as a global variable, and there is no control over the loading of the model. What happens when, say, have three different versions for the web server? Let's take a closer look. Let's say we have three models for our model server, and then use this process pool deployment. Three model per web server can quickly turn into, say, tens of instantiation of the model in memory. Without any optimization, a typical deployment can often encounter out-of-memory issue. And another issue with this kind of web server approach is that it is difficult to form inference pipeline. What do I mean by that? Let's say one of this kind of circle represents a machine learning model. In a typical user-facing ML application, model does not work in isolation. There are typically chains of operators that involve pre-processing and post-processing, or embedding lookup, visualization, and ranking. There are also cases where you need to split the request between different models to perform A/B testing. For example, we want to send 80% of the traffic to one of the model and 20% to the other. Sometimes you can use ensemble as a technique to improve accuracy of the prediction. Combining output from different models, either through averaging or voting, help combat model bias and to improve the performance. And more complex pattern is also possible as well. For example, to optimize end-to-end latency, we can try the input on a faster but simpler model. Only if the model output low confidence, we route the request to a heavier weights but more accurate models. Otherwise, we can just assume that since the model has given high confidence, we can just return the results. So in summary, a simple web server is great for demo, proof of concept. However, it requires a lot of additional optimization to make it production ready. When just a simple web server is not enough, people turn to the second approach. That is to offload the model serving to a specialized external service. Using our previous Flask server example, the API endpoint, when you receive the request, instead of passing it through TensorFlow, you'll now forward the request to some sort of external service. Here we represent it as the cloud. Example of this kind of services include TensorFlow serving from Google, Onyx Runtime from Facebook and Microsoft, Seldon, TensorRT from NVIDIA, as well as AWS SageMaker. Let's take a step back and look at examine this approach. When requests come in through HTTP, there are actually many steps before you reach the model for core inference bits, and many steps after the inference. When HTTP requests come in, it needs to be checked and validated, parsed, and transformed into transformed with custom business logic specific to the workload, and then to transform the input so that it can be run by the model. And then once you have the model inference, and the model output still need to be transformed and be applied with custom business logic, and finally result need to go out in an HTTP response format. What happened when we have external service? Originally, the entire sort of stack of steps happened in the web server on the left. When we offload the inference to external service, only the inference is shipped to external service. The input and output transformation span across the web server and external service. So in essence, I will characterize these external services as tensor-in, tensor-out. Their interface is pretty limited to just numeric tensor or some variant of it. For a concrete example, for image classification, when you take in bytes from API request, sort of decode it and then do some color normalization, and then like for image preprocessing, like cropping, and then convert it to 3D tensor, and then the output, put it through the model, and the output from the inference state is also a tensor. And then when you translate this tensor into some sort of English label or database ID, it is worth noting that some of the logic are tightly coupled with the model itself. When we improve the model accuracy, some of these pre or post-processing procedure might change. Additionally, the split between one part of the request handling logic and the other part of model inference logic brings a lot of complexity. So in summary, the external service approach encourages separation of concerns, but you do need to manage different services separately and tune them separately. More importantly, the model evaluation logic is not split from business logic. And the approach is hard to learn because of this sort of new custom system. And in addition, it's hard to debug because it's no longer the training framework or data scientist you are familiar with. You have to work with RPC, setting up external service configuration, or even different like computation system and deploy to those systems. Is there a better way? We build Reserve. Reserve leverage the RAID system to transparently scale the model to 100 cores. It gives end-to-end control over how the request is handled, as well, just like the web server approach, but the model is now isolated and scaled independently. Reserve is also pipeline native, will enable users to easily combine multiple models together and easily construct and connect these models. We also have built-in extensibility. It is a programmable serving system that allows you to modify how it works while it's running, as well as offering monitoring and observability out of the box. Let's take a closer look at the Reserve API. Models can be defined with a simple Python class. The model can be loaded in the init method. The call method sort of identifies the HTTP request handler. Reserve explores a Flask request interface so it's easy to use, understand, and migrate your existing Flask application. You can add arbitrary business logic, pre-processing or post-processing in this handler. The key is that model evaluation and surrounding business logic is in one place. Reserve has a concept of backend and endpoints. A backend is associated with model implementation and is versioned and scalable. For example, it can specify the number of replica in the create backend call. Endpoint is an user-reachable endpoint, and it is associated with one or more backends. Here we declare a HTTP route for that endpoint /API. So as a summary, we have sort of the class interface to define a backend. We have Flask requests, make it easy to sort of migrate your existing Flask application. The backend is a scalable individual units, and endpoint is a user-reachable HTTP endpoint. I call Reserve a programmable serving system. The concept of endpoint is associated with a logical service and reachable by URL route. Under endpoint, you can associate it with multiple different backends. Reserve has built-in support for composing model together because in your backend implementation, you can invoke method on the endpoints. Instead of configuring your service with YAML, Reserve's configuration language is just Python, the language and tool data scientists are familiar with. And by building on top of Ray, the distributed runtime allows us to update running cluster and make every single component fully fault tolerant. As we discussed, as compared to tensor-to-tensor system, Reserve give you end-to-end control over the request. Here's an example of how to implement a very basic PyTorch image classifier end-to-end. Reserve also has the ability to let you scale out, implement batching, as well as utilize custom GPU. Reserve is just a Python package. You can run it anywhere. We can run it on your laptop for quick demo and development. You can deploy it to a server. We'll have built-in template for you to run Reserve on Kubernetes, as well as all major public cloud. You can try it out today by just pip install and from Ray info serve. We have a vibrant community discussing serve in the Ray Slack. And you can check out our documentation at docs.ray.io. Also, recently I published several blog posts about Reserve, including one, how to use Reserve to deploy natural language processing model with Hugging Face. And you can check out this link to check it out. So the key takeaway for this talk is that there are two common approaches for model serving. You can wrap your model in web server, or there's this tensor-in, tensor-out specialized system. Both have their own flaws. Reserve is a web framework that bridges the benefits of the two approaches, scales the model to many machines, as well as grants the data scientist end-to-end control over the machine learning API. And thank you. I'm willing to take any question.